Hello, my name is Gary Conduff. I'm a first-year PhD student at Mississippi State University. This was more of a methodology research project that we conducted in the fall of 2012. We were wanting to evaluate the sequestration of Auxin herbicides in sprayer hoses. New transgenic herbicide-tolerant crop varieties may provide benefits to producers, with more alternative weed control options, decreased cost, and helping with resistance issues, such as different modes of action. With this will come the increased concern for issues such as herbicide drift, volatilization, and sprayer contamination. Synthetic Auxin herbicides mimic the physiological effects of plant growth regulators and cause abnormal growth and even mortality in broadleaf plant species. Cotton, soybeans, and other broadleaf crops are extremely sensitive to Auxin herbicides and show injury when exposed to trace amounts. When susceptible and synthetic Auxin-resistant crops are interspersed, there may be a high probability for application mistakes. Compounding this problem, synthetic auxins are extremely difficult to clean from spray equipment. Spray contamination caused by a failure to thoroughly clean a sprayer may cause crop injury up to several months after using the sprayer and following several subsequent applications. This can occur when herbicide residues adhere to a surface within the sprayer and subsequently brought back into a spray solution. Problems may occur, especially considering that glyphosate has been shown to be very effective at dissolving plant growth regulating herbicide residues in a sprayer. Dicamba has a dissociation constant, or a pKa, of 1.9. The way in which ammonia will work is it will increase the pH, which will increase solubility of herbicides. Dicamba has a water solubility initially of 4,500 milligrams per liter. Beer Boom in 2004 showed that dicamba residues, even when an ammonia water solution was used, had a subsequent percent use rate of 0.024% from the tank and 0.63% from the spray boom. The study was conducted in Wisconsin, and it was conducted using dicamba, in which they filled the tank full of a dicamba solution, sprayed it out, cleaned it with ammonia solution, and the next day came back in and filled the tank up with water, and this is where they got the subsequent percent use rates from. The objectives of this research project were 1. To develop a methodology to assess different cleanout procedures on different hoses and cleanout methods, and 2. To determine if dicamba persistence will differ among various hose types and cleanout procedures. Both Clarity and Roundup Weather Max were used in the same trial. All lines were filled with Clarity at 0.5 pounds acid equivalent per acre. All lines were incubated for 48 hours with the Clarity inside them. Lines were then flushed and cleaned with one of 2 different cleanout procedures: water cleanout and an ammonia cleanout. There were 5 different types of hoses used in this study. All hoses were 1/2 inch inside diameter. We had 3 hoses coming from John Deere, with 1 hose coming from Fox Equipment, which was a beverage dispenser, and 1 hose coming from the local co-op. The 3 hoses from John Deere were all comprised of different materials inside and out, with the number 1 hose in the picture here being comprised of PVC high tensile strength yarn, 1 ply. The number 2 hose in the picture would be the premium hose from John Deere, which was comprised of a linear low-density polyethylene blend. And the 3rd hose from John Deere would be number 4 in these pictures here, which was comprised of a PVC polyurethane high tensile strength yarn, 2 ply. The reason we went with the Fox Equipment hose was because it was highly touted as a hose that was easily cleanable, meaning that it left no residues whatsoever, and it was comprised of a polyester reinforced polyethylene with Glass Flex Plus. And the local co-op hose is a VersaGuard synthetic rubber hose. The hose tips and the initial setup of the hose tips, we probably need to begin with the length of the hose. Our hoses were all 10 foot in length, and we surmised through calculations that 10 feet at a 1/2 inch inside diameter will give us enough fluid and enough working fluid to cover a 40-foot length row or plot with 2 rows being sprayed. The initial setup of the hose tips began in this region right here with a barb inserted into the inside of the hose, a 1/2 inch reducer down to a 1/4 inch female coupling, which is all pneumatic. And then we had a band clamp that was tightened around the hose. So this occurred on each end of the hose, essentially trapping the fluid within the hose. For the initial spray line fill, we used a 2-row boom with 4 spray nozzles. Each nozzle was a TJet XR 80015. For the initial spray line fill, we also had a 3-gallon can hooked up to a CO2 tank, and we also had this line coming from the 3-gallon can that we would hook into our 10-foot of hose. I had a shutoff valve here that I would turn on once everything was hooked up, especially once the 10-foot hose was hooked up to the boom. Once everything was hooked up, what we would do is purge the air out of the boom. Any air that was left in the line we would purge out to get the solution to fill the line itself. Once the line was filled, we turned the shutoff valve off, and once the line was sufficiently filled, the line was disconnected with the solution remaining in the line. All lines were cleaned according to protocol, with all hoses being cleaned of one of 2 ways. 15 hoses were cleaned with an ammonia cleanout of 1% solution of 1 quart 25 gallons, or 1.28 ounces per gallon solution run through each hose, with 3 gallons total run through each hose. The reason we chose this number of 3 gallons was that it best represented a 250-gallon spray tank that was filled halfway. For 10 foot of that hose that the solution is running through, we surmised that about 3 gallons were actually running through that 10-foot section. The remaining 15 lines were cleaned strictly with 3 gallons of water run through each hose. All hoses were incubated with their designated cleanout for 24 hours. All lines were left empty for 48 hours after final cleanout flush. Spray lines were then filled with Roundup Weather Max at 1 pound acid equivalent per acre and incubated for 48 hours. Experimental layout was a 5x2 factorial on a randomized complete block, and it was replicated 3 times. Our plot size was 12.66 feet, 4 rows, by 40 feet. The 2 center rows of our 4-row plots received treatment, while the outside rows served as a buffer and a running check. This is a picture that illustrates what we tried to do when we were actually putting the final solution of the Roundup Weather Max in. You can see this bank right here. We had the shutoff valve going to the tank, and this is our CO2 regulator. These lines were directly hooked into this bank, and one thing that we probably need to improve on is putting a shutoff valve on each one of these hoses, because once we uncoupled this hose from the bank itself, the back pressure actually released everything back out of that hole. So that's something we need to work on in the future. This was just a test run right here, and we did not use this to fill. We were just seeing if it would actually work. We used soybeans as a bioindicator to assess cleanout efficiency in this project. Applications were made 6 weeks after initial emergence. 2-row boom with TJet XR 80015 were used. Applications were made at 15 gallons per acre, and we took weekly visual ratings at 7 and 14 days after treatment. This is an example of what we did in the field. This was Ryan Edwards helping me out one day, and he's actually hooking the line up to the CO2 tank or the regulator itself. What we had was a shutoff valve here. He would hook the line up, and then I would go through the plot and spray. Considering that the line itself is acting as the carrier of the solution, we had to hook the line directly into the CO2 tank regulator. So this is a close-up examination of the regulator and the shutoff valve and the hose itself. So here's the regulator. It's calibrated to deliver 136 milliliters in 15 seconds per nozzle. So we actually had to calibrate not the can that is usually in this area, but the hose itself acting as a carrier. Our results indicated that due to hose type, we did have significant difference with injury percentage. On the left-hand side of this graph, you'll see that injury percentage goes from 0 to 40%, and our hose types are on the x-axis. 7 days after treatment, we saw a significant difference from the green John Deere hose compared to that of the gray Fox Equipment hose, the yellow hose from John Deere, and the blue premium hose and the co-op hose from the local co-op. All were significantly greater than the check, which showed no injury. 14 days after treatment, the trend still stays true, but the injury percentage has gone down, and there is no significant difference between hose type, but when you compare the hose type with the check, there is significant difference based on injury and hose type. As far as the cleanout procedures, we found significant differences 7 days after treatment when comparing water cleanout to ammonia cleanout, with ammonia showing the greatest propensity to cause injury in the soybeans. In the second week of our visual ratings, we saw the same trend holding true, but there was no significant difference between the two cleanout procedures themselves. Here we can see some visual ratings from in the field. This was 7 days after treatment. All plots exhibited injury throughout the plot. Although not uniform and not consistent with a direct dicamba spray, injury was observed. Here's some more injury in the field. And finally, a last picture of injury in the field. For our conclusions, initial results showed that 7 days after treatment, hoses cleaned with ammonia resulted in significantly greater injury than those cleaned with water. Although 14 days after injury the trend did stand, it was not shown to be a significant difference. Injuries at 7 and 14 days after treatment were shown to be significantly different based on a hose type. We quickly realized that there could be an issue with boom contamination throughout the plots. So considering that we had running checks in each plot, we did not spray separate checks using both cleanout methods by hose type or hose variety. So in the future, we would like to try more hose types, possibly more cleanout procedures, separate checks for all cleanout procedures and hose types, and using both dicamba and 2,4-D in soybeans and cotton respectively. I'd like to thank the Mississippi Soybean Promotion Board for their future funding. I'd like to thank Mississippi State University, my advisor, Dr. Dan Reynolds, and my entire crew, including Elena Blaine, Jasper Cobb, Ryan Edwards, Amber Etchison, Camille Hayden, Chad Smith, and Reed Story.